Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. Okay, so question 1 just asks, what is Planck's equation? Okay, so I'll write it down here. Planck's equation. Okay, so Planck's equation can be simplified into E is equal to H times frequency. So E is the energy of a photon. And H is just Planck's constant. So I'll write down its value as well. Which is 6.626 times 10 to the negative 34 joules times second. And lastly, frequency is our last term. And frequency can also be calculated, if it's not given in the question, using the following equation. Where frequency is equal to C over lambda. So C is the speed of light. And its value, it's pretty easy to remember. It's 3 times 10 to the power of 8 meters per second. And lastly, lambda is wavelength. So wavelength can either be in nanometers or meters. Okay, so let's see what the junior tutor said. Max Planck discovered a theory that energy is transferred in the form of chunks called quanta, assigning as h. The variable h holds the constant value equal to 6.63 times 10 to the negative 4 joules times seconds, based on the International System of Units, and the variable describes the frequency in 1 over seconds. Planck's law helps us calculate the energy of photons when their frequency is known. If the wavelength is known, you can calculate the energy by using the wave equation to calculate the frequency, and then apply Planck's equation to find the energy. Planck's equation is given as E equals h times v, where h is Planck's constant, and v is the frequency in meters. Yep. I'm gonna write that the units of frequency is given as 1 over S. Frequency can be calculated I also just added that the units of frequency is given as 1 over S. Say as well. Frequency can be calculated by dividing the speed of light by the wavelength. Okay, so question number 2. The kW for water at 0 degrees is 0.12 times 10 to the negative 4. Calculate the pH of a neutral aqueous solution at 0 degrees. Okay, so let's say we had a solution of water, and I'll show it associating into its ions into H3O plus OH minus so if we look at this reaction, we can see that H3O plus and OH minus react at a 1-to-1 ratio. So the concentration of H3O plus should be equal to the concentration of our OH minus ion. So first, let's recall the Kw expression, where Kw is equal to the concentration of H3O plus times the concentration of OH minus. Okay, so like I mentioned earlier, if those two values are the same, then we can rewrite this expression as Kw is equal to the concentration of H3O plus, but squared. So let me just kind of insert that in between the two lines. And in the question, they give us the value for Kw. So all we have to do is plug it in. And then solve for our unknown, which is the concentration of H3O plus. Okay, so to isolate this, we just need to take the square root of both sides. So I'll show that here. And you should end up getting 3.5 times 10 to the negative 8 is equal to the concentration of H3O plus. Okay, so this is step 1 of answering this question. The second part is to calculate for the pH. So the equation for finding pH is equal to negative log of the concentration of H3O+. So since we already found this in the previous step, all we need to do is plug it in. So negative log of 3.5 times 10 to the negative 8, which gives us a pH value of 7.46. Of a neutral aqueous solution at 0 degrees. Okay, so let's see what the junior tutor said. Kw is the self-ionization constant of water, and it is calculated using the following formula. Kw is equal to H3O plus times OH minus, where H3O plus, the concentration of H3O plus is equal to the concentration of OH minus, and from the given, we can calculate the value of H3O plus. Okay, so they showed that the Kw is equal to the concentration of H3O plus squared, and then substituting the value of Kw, they got the 0.12 times 10 to the negative 14. Just is equal to H3O plus squared. They square rooted both sides to get 3.5 times 10 to the negative 8 moles per liter for the concentration of H3O plus. They plugged it into the pH equation and also got 7.46. Yep, so this solution is correct. Okay, so question 3 says to draw the structure of the organic product formed and the reaction of mCresol with sodium hydroxide. Okay, so let me write down the structure of mCresol. So it starts off with a benzene ring. It contains an alcohol group, and then in the meta position, there is a methyl group. Okay, and the question says that it reacts with sodium hydroxide. Okay, so if we look at both of these reactants, you'll notice that sodium hydroxide is a common base, and mCresol can actually act as an acid. So I'll show that this alcohol group has a proton that can be donated. So what happens is an acid-base reaction. And then we get the following products. So mCresol donates its proton and reacts with the sodium plus ion, and another, wait, let me just write this down here. And the second product would just be water. Okay, so let's see what the junior tutor said. Structure of mCresol can be derived from its IUPAC name, which is 3-methylphenol. When reacted with sodium hydroxide, it undergoes an acid-base reaction since the phenol is considered as an acid. Hence, the product is a salt, where sodium is substituted to the hydrogen of the hydroxyl group of mCresol. Below shows the reaction. Yep, so the name of the product is sodium 3-methylphenolate. Okay, so the solution is correct. Okay, so question 4. What is the standard enthalpy of formation for nitroglycerin? Express your answer using 4 significant figures. The explosive nitroglycerin decomposes rapidly upon ignition of sudden impact according to the balanced chemical equation. So let me write this down as well. So 4C3H5 N3O9. So this is the structure, the chemical formula of nitroglycerin. And then it decomposes to form carbon dioxide, water, and nitrogen. And oxygen. Okay, so luckily for us, the reaction is balanced already. And the question also gives us the enthalpy of reaction. So this whole reaction is negative 5,678 kilojoules. And they want us to find the standard enthalpy of formation for nitroglycerin. So to answer this question, first let's recall how to calculate the enthalpy of the reaction. So this is equal to the sum of N times the enthalpy of formation of our products. So N corresponds to how many moles there are of each substance. And then this is subtracted by the sum of N times enthalpy of formation of all of our reactants. Okay, so in the case of our question, I'll show what this equation would look like if we were to sub in all of the values. So first, I'll write down all of our products. So for our products, we have 12 moles of CO2. And this is multiplied by delta H of formation of CO2 gas. So I always like to write down what state they're in as well, because depending on the state, this will also affect its delta H of formation. So it's good practice to write down the states as you go along. Okay, so this is plus 10 times the delta H of formation of H2O liquid plus 6 times the delta H of formation of nitrogen gas. And then lastly, for our products, we have 1 mole times the delta H of formation of oxygen. Okay, so the equation doesn't end here because that was only our reactant side. We then have to subtract by the delta H of formation of reactants. Sorry, this was our product side, and then we have to subtract by the delta H of our reactants, which is only the nitroglycerin. So it's 4 times the delta H of formation of, I'll just write nitroglycerin. Okay, so before I look up all the standard enthalpy values, first let's recall when we have an element in their elemental state, such as nitrogen and the oxygen, they have N2 gas and N2 gas. Their enthalpies are equal to 0. So I'm just going to cross out their values from our equation. And then I'll just write like a note up here. When you have them in their elemental state, delta H of formation is equal to 0. Okay, so for our next line, I'm just going to sub in all of the values that we know. We know that delta H of reaction is equal to negative 5,678 kilojoules. And we're going to multiply 12 moles by the delta H of formation of CO2. So I'm just going to look up the table for standard enthalpies. And this is usually given in like the textbook or in the question. So let's just find CO2 gas. So its delta H value is equal to negative 393.5. And it is in kilojoules per mole. And then we're going to add 10 moles times the delta H of formation of liquid water, which is negative 285.8. Okay, so that whole thing is subtracted by 4 times our unknown, which is the delta H of formation of nitroglycerin. Okay, so now we just have to simplify this and solve for our unknown. So our left side, I'll just write as the same thing. And then if we multiply 12 times negative 393 plus 10 times negative 285.8, you end up with minus or 7,580. The units are just kilojoules. Can't write today. And now this is equal to negative 1,902 divided by 4, which is equal to negative 475.5 kilojoules per mole. Okay, so let's see what the junior tutor said. And I'll box in my final answer because it looks pretty overwhelming. So the heat of reaction, also known as the enthalpy of reaction, is the change in the enthalpy of a chemical reaction that occurs at a constant pressure. So it is a thermodynamic unit of measurement useful for calculating the amount of energy per mole either released or produced in a reaction. It can be calculated using the formula delta H of reaction is equal to the sum of N times the delta H of formation of our products minus the sum of N times the delta H of our reactants. So delta HF is the standard enthalpies of formation of the compounds, and N is the stoichiometric coefficient in the balanced chemical equation of the corresponding compound. Since the standard heat of reaction is already given, the standard enthalpy of formation of the nitroglycerin can be calculated by knowing the standard enthalpy of formation of the products in this equation. Okay, so they showed CO2 and H2O, and then they also showed that the enthalpy of formation for the elements in their elemental state will be 0. And then they substituted the values to the formula and ended up with negative 475.5 kilojoules per mole. Yep, so this solution is correct. And on to question 5. The diameter of the moon is 3,474,000 meters. How is this written in scientific notation? Okay, so let me write down this number. Okay, so when so my method of trying to convert such large or small numbers into scientific notation is that I add the decimal after the last number. So let me just write add decimal. And then I like to count how many spaces it needs to jump to move to the end of our value. So count number of spaces. So in the case of this number, starting from in between the 3 and the 4, I'm going to count 1, 2, 3, 4, 5, 6. And then step 4, or 3, sorry, is to write the scientific notation. So it's 3.474. And then instead of writing those 3 zeros, we just write 10 to the power of however many spaces that was, which is 10 to the 6. And then this is still in meters. So I'll just write like a note down here. When moving to the right, so we moved 6 spaces to the right. So our exponent is positive. And then when moving to the left, the exponent will be negative. Okay, so let's see what the junior tutor said. To write in scientific notation, we must leave 1 digit to the left of the decimal point, and the rest of the significant digits are written to the right of the decimal point. The number of places moved by the decimal point will be represented by a power of 10. The 3474 digits are all significant, so leaving 1 digit to the left of the decimal gives 3.474. Decimal point has been moved 6 places to the left. This is the same as dividing by a million. So 3.474 needs to be multiplied by a million to be equal to 3,474,000. Therefore, the scientific equation will be 3.474 times 10 to the power of 6. Yep, so the solution is correct. Great answer. Okay, so question 6. For a particular reaction, delta H is equal to 120.5 kilojoules. So let me write this down. And delta S is equal to 758.2 joules per Kelvin. And what is the delta G for this reaction at 298 Kelvin? Okay, so I wrote down all of the variables that were given. So to answer this question is actually pretty simple, since the delta G of formation, or the delta G of the reaction, can be calculated by taking the delta H and subtracting T times the delta S. So delta H is referred to as the enthalpy of the system. T is just temperature. and delta S is the entropy. Delta G is Gibbs free energy. Okay, so before we plug in all the values, I just want to double check to make sure that all the units should be kind of similar to each other so that everything can balance out nicely. So if we look at our enthalpy and entropy values, the enthalpy is in kilojoules and the entropy is in joules per Kelvin. So I'm just going to convert my entropy into kilojoules as well by dividing by 1,000. So 758.2 is also equal to 0.7582 kilojoules per Kelvin. Okay, so after that conversion, we can plug everything into the equation. Enthalpy is 120.5 kilojoules. T is just 298 Kelvin. And the delta S is 0.7582 kilojoules per Kelvin. So now our kilojoules should cancel out. And then we are left with our value, our Kelvin will cancel out, and we're left with our value in kilojoules, which is negative 105.44 kilojoules. Okay, so the junior tutor said that the Gibbs free energy of a system is a thermodynamic potential associated with a chemical reaction that can be used to do work. The change in the Gibbs free energy, delta G, that occurs during a reaction is equal to the difference in the change in the enthalpy of the system, delta H, and the change in the product of the temperature times the entropy of the system. Okay, so this can mathematically be expressed as the following. At constant temperature, this can be simplified. So calculating delta G for the reaction, delta G is equal to delta H minus T times delta S. And they also got negative 105.4. So since delta G is negative, we can say that the reaction is spontaneous when temperature is equal to 298. Yep, so this solution is correct. Okay, so question 7. Select the properties of the SN1 reaction mechanism. So they give us all these different properties. A, stereospecific, so this means 100% inversion of configuration at the reaction site. B, not stereospecific. C, bimolecular at rate determining step. D, unimolecular at rate determining step. E, rate is governed by steric effects. Or F, rate is governed by the stability of the carbocation that is formed. Okay, so first I'll just show a typical SN1 reaction, which is also known as a nucleophilic substitution reaction. So typically this takes place in 2 steps. So first we have, let's just say R binded with L. So this is our substrate. And for the first part of the mechanism, we have L, which is our leaving group. Which is removed. And we're left with R plus L minus. Okay, so I'll also just write down that R plus is considered as our carbocation. So this just means like a positively charged carbon group. And L is our leaving group. Okay, so step 2 of this reaction is when we have our carbocation that reacts with a nucleophile that can be like a halide. So this is our nucleophile. Okay, so the negative charge comes in to neutralize the positive charge of our carbocation. And then we are left with our product. Okay, so now let's go over all of the options that they give us. So is this reaction stereospecific, where 100% of the conversion, 100% inversion of configuration at the reaction site, or is it not stereospecific? So the answer is that it's B. So it is not stereospecific. And the reason for this is because our nucleophile can attack from any side. So for the next section, is it bimolecular at a rate determining step or unimolecular at a rate determining step? So the answer is D. It is unimolecular. And this is because our reaction is only first order. And lastly, is the rate governed by steric effects, or is the rate governed by the stability of the carbocation that is formed? So the answer is F. The rate is governed by the stability of the carbocation that is formed. Okay, so I'll kind of explain this. Step 2 would be considered our rate determining step. So as you can guess, that means that it's the step where the rate is determined by. So in this case, if our carbocation, which is R+, is stable, then the reaction is a slow reaction. Well, it would be slower because a nucleophile wouldn't want to attack something that is stable. So that reaction that forms our product would be slower. But if the carbocation was unstable, then the reaction would take place faster and make us more product. So typically the carbocation is most of the time stable, unless it was more stable with like another group attached to it. And the junior tutor said that the given mechanism is not stereospecific, since the carbocation that is formed gives a planar structure which allows for attack from either side. It is also unimolecular because the rate determining step, which is the formation of the carbocation, does not need help from the nucleophile. Steric effects do not play any specific function because the carbocation is planar, and the stable carbocation disperses the positive charge throughout the molecule. So they had B, D, and F. So this solution is correct. Okay, so question 8. Several alkene compounds are given below. Indicate if each compound can exist as stereoisomers. Okay, so I'll write down the definition of stereoisomers. This is when two compounds have the same formula but different orientation of atoms. Okay, so let's look at our two options. So for part A, we have a double bond in between two carbon groups. So this can be written like the following, where we have a methyl group on one side, the double bond, and then the methyl group on the other side. So this is the trans configuration. And another way we can draw this is having the two methyl groups on the same side to form the cis configuration. Okay, so these can exist as stereoisomers. Now let's look at E. So similarly, we have a double bond But this time there's also a bromine and an ethyl group as well. So this can be written as having our methyl group on one side or the different configuration can have this side as the same, but our ethyl group on the same side as our methyl group, and the bromine on the same side as the hydrogen. Okay, so let's see what the junior tutor said. Stereoisomers are isomers that differ only in the spatial orientation of their component atoms. Possible structures are shown below. Okay, so they drew the same kind of products. It can be observed that the compound has two isomers, one in which the two methyl groups are on the same side, while the other one is on the opposite sides. Hence, the compound can exist as stereoisomers. Next is the possible structure of our second compound. So here they show the bromine on the same side as the methyl, or they show the ethyl group on the same side as our methyl. Here the ethyl group and bromine can be interchanged in their positions. Hence, the compound can also exist as stereoisomers. Okay, so this solution is correct. Okay, so next we'll move on to question number 9. What is the chemical equation for cellular respiration? Okay, so briefly, glucose is reacted with oxygen to form carbon dioxide plus water. Okay, so now I'll just sub in the chemical formula. So the chemical name for glucose, C6H12O6. Oxygen is O2. Carbon dioxide, CO2. And water is H2O. So to balance this equation, let's balance the carbons first. So we have 6 carbons on our reactant side. So I'm going to add a coefficient of 6 in front of our carbon dioxide. And notice that oxygen is present in both carbon dioxide and water. So I'm not going to balance the oxygens just yet. I'll balance out the hydrogens. So in our reactant side, there are 12 hydrogens. So I just need to add a coefficient of 6 in front of the H2O. So now we have 12 plus 6, which is 18 oxygens. So on our left side, we just have 6. So that brings it back down to 12. So to balance this, I would just need to put a 6 in front of my O2. Okay, so let's see if everything is balanced. We have 18 oxygens on our reactant side. 12 plus 6, also 18. 6 carbons and 12 hydrogens. Okay, so the junior tutor said that cellular respiration is the process in which cells break down molecules for energy. In order to do this, the cells use oxygen and produce carbon dioxide. It is an aerobic process in which living cells break down glucose to release energy in the form of ATP, which is adenosine triphosphate. Overall, this 3-step process involves glucose and oxygen reacting to form carbon dioxide and water. Chemical equation can be represented as C6H12O6 plus O2 makes CO2 plus H2O. When we balance the chemical equation, you get the glucose plus 6 oxygens makes 6 carbon dioxide plus 6 water molecules. Okay, so this solution is correct. Great answer. Okay, so question number 10. Is benzoic acid polar? Okay, so first let's write down the structure. A benzoic acid. Let's just break down the name. So benz tells us that there is a benzene group involved. So if you don't remember what benzene looks like, it's a 6-membered aromatic carbon ring. So that means there's a double bond in between every other carbon. And when something ends in ic acid, that means there's a carboxylic acid functional group as well. Which would look like this. So that tells us that the structure of benzoic acid contains benzene and then a carboxylic acid group attached to it. Okay, so this question can be kind of tricky, and the reason for that is that the benzene group is considered nonpolar because all of the carbon and hydrogen groups are like they have similar electronegativities. So there's no dipole moment if we just had a benzene ring on its own. But however, if we look at our carboxylic acid groups, they contain the oxygen-hydrogen and oxygen-carbon bonds, which are polar. So if you were to describe the polarity of benzoic acid, it is considered slightly polar. So it's one of those groups that doesn't really have like a definite answer whether or not it's exactly polar or non-polar, just because it has that large aromatic non-polar group. But it also has polar functionalities. But overall, it's not completely nonpolar because we have a non-zero dipole moment in the direction of the more electronegative oxygen atoms. So the junior tutor said that benzoic acid is polar in nature, however, it is only slightly soluble in cold water. Carboxylic acid group is what's making the benzoic acid polar, and the bulk of the benzoic acid molecule is nonpolar due to a large carbon, not really chain, more like a ring. So I'll say this solution is correct. Benzoic acid is considered slightly polar since the carboxylic acid group and the large benzene group is nonpolar. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, then please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And if you enjoyed today's video, you can go ahead and leave it a thumbs up and a comment. And don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.